The fury of the ocean during a storm is a sight to behold. Towering waves, howling winds, and the sheer power of nature unleashed. With today's technology, even large-sized ships can remain stable in these extreme weather conditions. Moreover, some ships, designed by engineers, have the capability to self-right themselves when overturned by waves. But have you ever wondered why, despite the huge, disastrous waves, large ships can withstand the onslaught and stay afloat? Here is why monster waves can't sink large ships during storms. Today's technology. We often marvel at the remarkable stability of large-sized ships, such as cargo vessels weighing hundreds of thousands of tons, as they withstand the fury of massive waves. When a ship sets sail on the open sea, it is exposed to a multitude of forces and pressures from the waves and wind, which can pose a significant threat to its stability. In order to survive and navigate through treacherous waters, a multitude of things play their parts. All ships are also equipped with a sophisticated ship stability system, which is essentially the ship's balance when floating. This system enables the ship to self-correct and stand upright again when rocked by waves or wind. To achieve this remarkable stability, several devices are employed, including bilge keels. Bilge keels have a distinctive wing or fin-like shape that is stationary and installed on the side of the ship's hull, spanning approximately 2/3 of the ship's length. As the ship gains speed, the stability effect of the bilge keels increases, providing a steady and reassuring presence in turbulent waters. Another crucial type of stability device is the anti-rolling tank, a specialized tank that functions to stabilize the ship's position when it tilts to the left or right. Installed across the width of the ship, this tank is designed to counteract the rolling motion of the vessel. When the ship tilts, water in the tank flows, significantly reducing the rolling motion and maintaining the ship's equilibrium. The anti-rolling tank itself has two types, active and passive. In an active rolling tank, the mechanism for water flow in both tanks is more complex and utilizes a pump, providing an additional layer of stability and control. These modern shipbuilding techniques and materials have also contributed to the enhanced stability of large-sized ships. Advanced computer simulations and modeling enable engineers to design and optimize ship hulls for maximum stability, while high-strength materials and robust construction methods ensure that the ship can withstand the most extreme weather conditions. The implementation of advanced navigation systems and weather forecasting technologies has significantly improved the ability of ships to anticipate and prepare for adverse weather conditions, further reducing the risk of instability or capsizing. The combination of cutting-edge technology, innovative design, and robust construction has made it possible for large-sized ships to remain stable and unsinkable even in the most challenging maritime environments. This takes us to the next type of stability device: active fin stabilizers. The next type of stability device is the active fin stabilizer, a sophisticated device shaped like a fin, designed to dampen the rolling or tilting motion of the ship. Have you ever wondered about the forces at play when traveling in a car? Try this simple experiment. Open the window and put your hand out with all fingers together, facing forward with your palm facing the road. Ensure your fingers are straight and your hand will remain steady, experiencing no force above or below your fingers. This is an example of drag, a fundamental concept in aerodynamics. Now slightly lift your fingers upwards and observe what happens. You'll notice a lift force under your fingers, causing your hand to tend upwards. This is called a positive lift. Conversely, when you put all your fingers downwards, a push force emerges on top of your hand, causing it to tend downwards. This is known as a negative lift, or downward lift. Notice how the speed of the car affects these forces? Slow down the car and repeat the steps. You'll see that the lift and push forces are significantly reduced, demonstrating that drag speed is crucial for achieving a substantial lift or push. This simple technique illustrates the basics of drag, positive lift, and negative lift, essential principles for understanding the function of aerofoils or hydrofoils, such as fin stabilizers used on ships. Fin stabilizers found on many vessels, rely on these principles to counteract rolling motions and enhance stability. By manipulating the angle of attack and speed, fin stabilizers generate lift forces that oppose the rolling motion, ensuring a smoother ride. The experiment with your hand out the car window may seem simple, but it demonstrates the fundamental forces at play in aerodynamics and hydrodynamics, which are critical for designing effective fin stabilizers. Installed on both sides of the ship's hull, the fin stabilizer can move in various directions, controlled by the ship's highly sensitive gyro system. This advanced system ensures precise and swift responses to changes in the ship's movements. When the ship is rolling or tilting, the ship's sensitive gyro system sends a signal to the activating system in the form of electrohydraulics, which promptly adjusts the fin stabilizer to counteract the motion. However, it is important to note that active fins are not very effective when the ship is traveling at speeds below 10 knots or about 18 kilometers per hour. At such low speeds, the fin stabilizer's ability to dampen the rolling motion is significantly reduced, and alternative stability measures may be necessary. On container ships, there is an additional stability system, known as the anti-howling system. This servo control system is designed to keep the ship horizontal during loading and unloading at ports, ensuring safe and efficient cargo operations. The anti-howling system cannot be used as a stabilization system in open seas and can only be used when the ship is at port, loading and unloading containers. This system is specifically designed to detect the angle of inclination of the ship and automatically balance it by pumping water into the ballast tank from right to left, or vice versa. The anti-howling system consists of a main control panel, pump start panel, and anti-howling pump, allowing for both automatic and manual operation. Its performance is crucial in maintaining the ship's stability during cargo handling operations. A ship's stability system is significantly influenced by its balance points, which determine the magnitude of the ship's stability. Understanding these balance points is essential for ship designers and operators to ensure optimal stability and safety in various operating conditions. Although the combination of cutting-edge technology, innovative design, and robust construction has made it possible for container ships to maintain exceptional stability and safety in various operating conditions, it's still not possible without the crew playing a crucial role, which takes us to the ship's balance point and the utilization of SAR, operations, and the crew. The ship's balance points must always be considered by the crew, as neglecting to account for stability calculations is a primary cause of accidents, whether the ship is at sea or in port. This oversight can have devastating consequences, resulting in the need for search and rescue operations. Rescue ships play a critical role in providing assistance to victims of maritime accidents at sea. However, during these rescue efforts, extreme weather conditions and high sea waves can hinder SAR operations and potentially cause the ship to capsize. To address this challenge, engineers from around the world have developed innovative rescue ships with the concept of self-righting boats. These remarkable vessels are capable of returning to their original position even when flipped 180 degrees. In addition to being able to right themselves, self-righting boats can achieve high acceleration and withstand various extreme sea conditions, making them invaluable assets in maritime rescue operations. Many companies manufacture these self-righting boats, one of which is the esteemed Royal National Lifeboat Institution located in the UK. The creation of self-righting boats involves several crucial elements. Firstly, the initial design of the ship is critical, where all heavy equipment and objects must be positioned as low as possible within the ship to minimize the center of gravity. Secondly, the crew's operational and control area must be lightweight, strong, and filled with air to provide buoyancy. Additionally, the access door for the crew must be watertight to prevent water from entering the space when the ship is capsized. Self-righting boats also feature a sophisticated pendulum system designed to prevent water from entering the ship's interior. During operation, when the self-righting boat capsizes, the weights in the pendulum system hang vertically, causing all open sections to automatically close and prevent water from entering the ship. Furthermore, these self-righting boats are equipped with an onboard system that detects if the boat is capsized. This system automatically protects the boat by shutting down the radar and engines before righting the boat back to its original position. Once the boat returns to its normal position, the radar and engines restart. Moreover, crew members inside the boat must be seated and secured with safety belts to ensure their safety during a capsizing event. This comprehensive design and safety features enable self-righting boats to operate effectively in extreme conditions, providing a lifeline to those in distress at sea. The old ways: ballast water and ships. Ships have always required ballast to operate successfully and safely. For millennia, ships carried solid ballast in the form of rocks, sand, roof tiles, and many other heavy materials. From the 1880s onward, ships increasingly used water for ballast, thereby avoiding time-consuming loading of solid materials and dangerous vessel instabilities, resulting from the shifting of solid ballast during a voyage. Today, vessels carry ballast that may be fresh, brackish, or salt water. About 80% of the world's trade volume is transported by ship. Thus, global shipping is the underpinning of the majority of world trade. Unfortunately, in many instances, half of a given voyage must be undertaken in ballast to compensate for the absence of cargo. The etymology of the word ballast, meaning useless load in Middle Dutch. Ballast water is carried by many types of vessels and is held in a variety of tanks or holds. The relative complexity of ballast operations depends on the size, the configuration and requirements of the ship, and on the complexity of its pumping and piping systems. Ballast capacity can range from several cubic meters in sailing boats and fishing boats to hundreds of thousands of cubic meters in large cargo carriers. Typical vessel types and their ballast needs can be broadly classified. There is a wide range of ballast tank locations and configurations. The capacity, location, and flexibility of use of ballast tanks is a focal point in ship design. Consideration of required drafts and trim, hull loading limitations, and required vertical center of gravity establishes the necessary ballast volume and location. Because of different cargo distributions or fuel and water quantities on board, sister ships can have different ballast needs, even though the locations and sizes of the ballast tanks are identical. Ideally, ship owners prefer to complete all voyages with cargo. However, many trades and voyages require passage without cargo or in a light cargo condition. For example, a crude oil tanker or iron ore carrier typically transports a single cargo load between two ports, then returns to its point of origin or another port without cargo. In this empty condition, the vessel requires ballast to operate safely, a condition referred to as being in ballast. In contrast, a container ship may be fully loaded between two ports, but may then proceed with only a partial load between the next two ports. This vessel therefore sails with some cargo and some ballast, that is, with ballast. Since fuel costs usually increase with displacement, ship owners tend to use as little ballast as is necessary for the ship's safe, efficient passage when operating either with ballast or in ballast. Ballast water plays a crucial role in ensuring the safe operation of vessels during a specific voyage or portion of a voyage. By taking on board the right amount of ballast water, ships can achieve the required stability and operating conditions. Proper ballasting serves several essential functions, including reducing stresses on the hull of the ship. This is achieved by distributing the weight of the ballast water in a way that minimizes the strain on the hull, thereby preventing damage and ensuring the structural integrity of the vessel. In addition to reducing hull stress, proper ballasting also provides for transverse stability. This is critical for maintaining the ship's balance and preventing capsizing. Ballasting aids propulsion by controlling the submergence of the propeller. By adjusting the amount of ballast water, ships can optimize the propeller's performance, leading to improved fuel efficiency and maneuverability. Moreover, ballasting helps to submerge the rudder, reducing the amount of exposed hull surface, also known as freeboard or windage. This enhances the ship's ability to steer and respond to changing conditions. Another important function of ballasting is to compensate for weight lost from fuel and water consumption during a voyage. As a ship consumes fuel and water, it loses weight, which can affect its stability and operating conditions. By taking on ballast water, ships can maintain the required weight and balance, ensuring safe and efficient operation. The ballast condition, including when and how much water is loaded, is carefully determined by ship's officers based on the specific vessel's operating needs. This critical decision-making process requires expertise and attention to detail to ensure the safe and successful completion of a voyage. The major purposes of ballasting a vessel for a voyage are to increase its manageability and safety, particularly under heavy weather conditions, control its draft and trim for maximum efficiency, and control its stability to ensure safe passage. Ships must also be deep enough in the water to ensure safe passage, particularly in heavy weather. If the bow of the ship is not deep enough, the ship's forefoot will emerge periodically from the water surface. This leads to slamming, or heavy impact, of the hull when the bow hits the water with a high velocity on re-entry. Excessive slamming can lead to hull structural damage or even to hull failure and ship loss in extreme conditions. In heavy weather conditions, the ship's master usually chooses to decrease speed, which reduces the rate of occurrence and severity of slamming. Deeper drafts forward will generally reduce the tendency for the ship to slam. Typically, ships ballast to a light ballast draft in normal weather, then ballast to a deep ballast draft in heavy weather. Efficient propeller operation usually requires the propeller to be immersed, even in calm water conditions. Thus, if the stern is not deep enough, ballast may be needed to trim the vessel. Further, if the stern draft is not sufficient in rougher sea conditions, the ship's propeller will increase its revolutions per minute when it emerges from the water and will slow down when it re-enters the water. This causes engine control problems and increased loading on the propeller shafting and machinery. Increasing stern drafts reduces the tendency for the propeller to emerge and thus reduces racing. Designs typically seek to achieve a stern draft in heavy ballast of about 80% of the load draft. Accordingly, safe ship operation in heavy weather requires the addition of ballast to designated cargo holds, ballast holds, or tanks to achieve a heavy ballast load condition. The history of ship stability. Ship stability is an area of naval architecture and ship design that deals with how a ship behaves at sea, both in still water and in waves, whether intact or damaged. Stability calculations focus on centers of gravity, centers of buoyancy, the metacenters of vessels, and on how these interact. Ship stability, as it pertains to naval architecture, has been taken into account for hundreds of years. Historically, ship stability calculations relied on rule-of-thumb calculations, often tied to a specific system of measurement. Some of these very old equations continue to be used in naval architecture books today. However, the advent of calculus-based methods of determining stability, particularly Pierre Bouguer's introduction of the concept of the metacenter in the 1740s ship model basin, allowed much more complex analysis. The master shipbuilders of the past employed a time-tested system of adaptive and variant design, where tried-and-true ship designs were often replicated from one generation to the next with only minor modifications. This approach allowed them to avoid serious problems and ensure the stability and seaworthiness of their vessels. By building upon proven designs, shipbuilders could refine and improve their craft, gradually incorporating new innovations and techniques. This incremental approach to design allowed for the gradual evolution of shipbuilding, with each new generation of shipbuilders learning from the successes and failures of their predecessors. In contrast, modern shipbuilding has embraced a far more analytical and scientific approach to design. The advent of computational fluid dynamics, ship model testing, and a deeper understanding of fluid and ship motions has enabled shipbuilders to create vessels that are optimized for performance, efficiency, and safety. This shift towards a more analytical design process has allowed shipbuilders to push the boundaries of what is possible, creating larger, more complex, and more specialized vessels than ever before. One of the key innovations in ship design has been the introduction of transverse and longitudinal waterproof bulkheads. These critical structural elements were first introduced in ironclad designs between 1860s and the 1880s, with anti-collision bulkheads having been made compulsory in British steam merchant ships prior to 1860. The addition of these bulkheads has revolutionized ship design, allowing vessels to survive even in the event of significant hull damage. By limiting flooding to the breached compartments, transverse bulkheads increase the likelihood of ship survival, giving crews precious time to respond to emergencies and prevent catastrophic failures. Longitudinal bulkheads serve a similar purpose, but their design must take into account the potential stability effects of damage. If not properly designed, longitudinal bulkheads can exacerbate healing and stability issues, potentially leading to catastrophic consequences. Today, most ships feature advanced systems that enable the equalization of water between sections of the port and starboard sides, helping to limit structural stresses and changes to the ship's heel or trim. These sophisticated systems allow ships to maintain stability and balance, even in the face of significant damage or flooding. The evolution of ship design has been a gradual process, shaped by centuries of innovation, experimentation, and refinement. From the adaptive and variant designs of the past to the analytical and scientific approaches of today, shipbuilders have continually pushed the boundaries of what is possible, creating vessels that are safer, more efficient, and more capable than ever before. Add-on stability systems. Add-on stability systems are designed to reduce the effects of waves and wind gusts. They do not increase a vessel's stability in calm seas. The International Maritime Organization, International Convention on Load Lines, does not cite active stability systems as a method of ensuring stability. The hull must be stable without active systems. For instance, the bilge keel is a critical structural element employed in ship design, consisting of a long, often V-shaped metal fin that is meticulously welded along the length of the ship at the turn of the bilge. This strategic placement serves to enhance the vessel's stability and hydrodynamic performance. Bilge keels are typically employed in pairs, with one fin installed on each side of the ship, working in tandem to maximize their effectiveness. In rare instances, a ship may be equipped with more than one bilge keel per side, further emphasizing the importance of this design feature. The primary function of bilge keels is to increase hydrodynamic resistance when a vessel rolls, thereby limiting the amount of roll and maintaining stability. By introducing a carefully calibrated amount of drag, bilge keels counteract the rolling motion, ensuring that the ship remains upright and on course. This is particularly crucial in adverse weather conditions or when navigating through treacherous waters where excessive rolling can compromise the vessel's safety and operability. The V-shaped design of bilge keels is a deliberate choice, optimized to maximize their hydrodynamic effectiveness. The angled profile deflects the water downward, creating a region of higher pressure above the keel and a region of lower pressure below. This pressure differential generates a stabilizing force, opposing the rolling motion and maintaining the ship's equilibrium. By carefully controlling the shape and size of the bilge keels, naval architects can fine-tune the vessel's stability characteristics, ensuring optimal performance in a wide range of operating conditions. Added to their stabilizing function, bilge keels also play a role in reducing the stress and fatigue experienced by the ship's hull. By limiting the amount of roll, bilge keels minimize the cyclic loading and unloading of the hull structure, thereby reducing the risk of damage and extending the vessel's lifespan. This is particularly important for ships operating in harsh environments or engaging in high-stress activities, such as cargo ships or naval vessels. Another add-on stability system are the outriggers. The outriggers are a specialized design feature that may be employed on vessels to mitigate the effects of rolling, thereby enhancing stability and operability. These outriggers function by leveraging either the force required to submerge buoyant floats or the hydrodynamic properties of foils, effectively counteracting the rolling motion and maintaining the vessel's equilibrium. In certain instances, these outriggers are of sufficient size and significance to classify the vessel as a trimaran, a distinct category of ship design characterized by the presence of 3 parallel hulls. On other vessels, however, these outriggers may simply be referred to as stabilizers, underscoring their primary function of reducing roll and enhancing overall stability. The use of outriggers as a stabilizing mechanism is rooted in the principles of hydrodynamics and buoyancy. By extending beyond the main hull, outriggers increase the vessel's overall beam, thereby reducing the likelihood of capsizing and minimizing the impact of rolling. In the case of buoyant floats, the force required to submerge these elements generates a stabilizing moment, opposing the rolling motion and maintaining the vessel's upright posture. Similarly, hydrodynamic foils mounted on outriggers can produce a lift force, counteracting the rolling motion and enhancing stability. The design and implementation of outriggers vary widely depending on the specific vessel and its intended application. In some cases, outriggers may be fixed in place, providing a permanent stabilizing influence. In other instances, they may be retractable, allowing for greater flexibility and adaptability in varying operating conditions. The size and shape of outriggers also vary, ranging from slender, wing-like foils to larger, more buoyant floats. Regardless of their specific design, however, outriggers play a critical role in enhancing vessel stability and operability, particularly in adverse weather conditions or high-stress environments. Another example are the anti-roll tanks. Anti-roll tanks are a specialized type of interior tank designed to mitigate the adverse effects of rolling on a vessel. Fitted with strategically placed baffles, these tanks are engineered to slow the rate of water transfer from the tank's port side to its starboard side, thereby reducing the destabilizing influence of the free surface effect. By cleverly manipulating the flow of water within the tank, anti-roll tanks create a stabilizing force that counteracts the rolling motion, enhancing the overall stability and operability of the vessel. The innovative design of anti-roll tanks is rooted in the principles of fluid dynamics and vessel stability. By trapping a larger amount of water on the vessel's higher side, these tanks create a counterbalancing force that opposes the rolling motion, effectively reducing the amplitude of the roll. This is achieved through the careful placement of baffles, which impede the flow of water between the tank's port and starboard sides, thereby slowing the transfer of fluid and minimizing the destabilizing influence of the free surface effect. The implementation of anti-roll tanks requires meticulous attention to detail and a deep understanding of vessel dynamics and hydrodynamics. Engineers must carefully consider factors such as tank size, baffle configuration, and vessel operating conditions when designing these systems, ensuring that they provide optimal stability and performance. The anti-roll tanks must be integrated with the vessel's overall stability system, taking into account the interactions with other stabilizing elements, such as fin stabilizers or bilge keels. The benefits of anti-roll tanks are numerous, offering improved stability, reduced roll, and enhanced operability in adverse weather conditions. By minimizing the free surface effect, these tanks enable vessels to maintain their stability and balance even in rough seas or during high-speed maneuvers. These innovative tanks can expand the range of operating conditions for vessels, allowing them to navigate through challenging environments with increased confidence and safety. Gyroscopic internal stabilizers. The battle for ships to stay afloat in the unforgiving waves after waves of the monstrous sea has been a long and difficult one that has required so many innovative designs and approaches, which takes all the way back to the 1900s. During the period between 1920s and 1930s, the pioneering use of gyroscopes to control a ship's roll was created, when they were first employed on warships and passenger liners. One of the most ambitious applications of large gyros to control a ship's roll was on the Italian passenger liner, the SS Conte di Savoia. This innovative system featured 3 large Sperry gyros mounted in the forward part of the ship, which successfully reduced roll during westbound trips. However, the system had to be disconnected on the eastbound leg due to safety concerns. With a following sea, the vessel tended to hang with the system turned on, and the inertia generated made it harder for the vessel to right herself from heavy rolls. Gyro stabilizers are complex systems that consist of a spinning flywheel and gyroscopic precession, which imposes boat-riding torque on the hull structure. The angular momentum of the gyro's flywheel is a critical measure of its effectiveness, as it determines the extent to which the flywheel will continue to rotate about its axis unless acted upon by an external torque. The higher the angular momentum, the greater the resisting force of the gyro to external torque, resulting in a greater ability to cancel boat roll. A gyroscope has 3 axes: a spin axis, an input axis, and an output axis. The spin axis is the axis about which the flywheel is spinning and is typically vertical for a boat gyro. The input axis is the axis about which input torques are applied, with the principal input axis being the longitudinal axis of the boat, since that is the axis around which the boat rolls. The principal output axis is the transverse axis, or the athwartship, about which the gyro rotates or precesses in reaction to an input. When the boat rolls, the rotation acts as an input to the gyro, causing the gyro to generate rotation around its output axis, such that the spin axis rotates to align itself with the input axis. This output rotation is called precession, and in the boat case, the gyro will rotate fore and aft about the output or gimbal axis. Angular momentum is the measure of effectiveness for a gyro stabilizer, analogous to horsepower ratings on a diesel engine or kilowatts on a generator. In modern designs, the output axis torque can be used to control the angle of the stabilizer fins to counteract the roll of the boat, allowing for a smaller gyroscope to be used. This innovative concept was first proposed in 1932 by Dr. Alexanderson, a General Electric scientist. He suggested using a gyro to control the current to the electric motors on the stabilizer fins, with the actuating instructions being generated by therotron vacuum tubes. This groundbreaking idea paved the way for the development of modern gyro stabilizers, which have revolutionized the field of ship stabilization. Thanks for watching. See you in our next video.